Good morning, everyone. And I'm Jinhan Zhao from University of Electronic Science and Technology of China. And today I will talk about a plug-in OCT module for detecting laser welding. Uh, so laser processing technology is widely used in industrial manufacturing and medical fields. In automotive industry, lasers are widely used for tasks like welding car bodies and transmission components. This offers incredible precision and strength, making vehicles lighter and more efficient. And in aerospace, lasers are used to join large skin panels on aircraft, which helps reduce weight without compromising structural integrity. They're also key in assembling similar components of the aircraft, improving both accuracy and safety. Next is the role of lasers in battery manufacturing, specifically in lithium batteries. So here we use laser ablation is used to precisely remove unwanted material layers, improving both the efficiency and quality of battery production. And for medical applications, lasers were used in areas where retinal detachment treatment by carefully welding the retina to the eye wall, which is a highly precise, non-invasive procedure. It minimizes risk to surrounding tissues, making it safer for patients. And lasers are also gaining traction in bone surgeries. Laser cutting allows for more precise and less invasive operations, reducing patient recovery time and enhancing surgical outcomes. So let's first look at the image on the left, which shows our experimental setup. In this setup, laser and OCT, which means optical coherence tomography, are aligned coaxially and directed into the keyhole during the process. Below the photo, you can see the real-time data of the keyhole depth that we have collected. However, there are currently three major limitations with this equipment. First is that current methods requires a customized dichroic camera in the laser head, making the development of OCT products highly dependent on laser head design. This dependence hinders the independent development and the wider application of OCT products in laser processing monitoring. The second is that retrofitting existing laser heads with OCT monitoring requires opening the laser head, installing the dichroic camera, and tuning the optics, which is very time-consuming and risks damaging the laser head. The last one is shooting the probe beam through the thick focus lens degrades signal strength and introduce dispersion issues. So to attack these issues, we propose a laser head independent OCT module that functions as a plug-in component. This design avoids interface with the laser head and works fully independently. Tests scanning the surface of the leaf molten pool demonstrate that feasibility of this plug-in-and-play solution for new independent OCT products and upgrading existing laser heads with OCT functionality, providing seamless integration and maintaining performance quality. So in this new design, a beam with a central wavelength of 1310 nanometer OCT is used and placed under the laser head. A new dichroic camera, which we call DM2, was introduced. Again, placed at a 45-degree angle relative to the main axis of the laser head and parallel to the angle relative to the main axis of the laser head and parallel to the diameter DM1. DM2 is characterized by reflecting a passing center wavelength of 310 nanometer while passing 164 nanometer. After passing through DM2, the laser and the OCT beam were coupled into a single beam and focused at the same point on the simple surface. The the right figure illustrates the transmission and the reflection performance of DM2 across different wavelengths and angles. For the laser at 1064 nanometer, the transmittance is approximately at 90%, meaning that around 10% of the energy is reflected. Consequently, when our system is used on actual production, additional energy is required to compensate for this loss. This picture shows the results of 1.5 second laser irradiation on a metal plate, capturing process initiation to termination. The molten pool surface characteristics and the fluctuations are clearly discernible. Initially, the molten pool forms and rapidly expands outward. OCT signals before irradiation were stable, but were significantly affected by strong radiation once the laser was activated. A pronounced signal at 133 milliseconds indicates keyhole formation, shown by the OCT beam's entry into a deeper region. We speculate that this shadow in the right figure corresponds to the molten pool area. These observations confirm our plug-in OCT SIM capability to monitor the laser welding process effectively, capturing oscillations, deep variations, and keyhole formation. In conclusion, our research achieved two goals. The first is the development of a plug-in OCT module. The paper introduced a novel plug-in OCT system for real-time in situ monitoring of laser processing, overcoming the limitation of existing OCT integration methods. Two is that laser head independent design. The OCT model offers a plug-and-play solution capable of seamless integration with various laser systems, enhancing its flexibility and applicability. However, there are still some challenges remain. The signal from the molten pool was detectable, where the signal from the keyhole remained unclear. Post-experiment analysis revealed the damage to the dichroic mirror in DM2, evidenced by the welding film deposits on its surface. So our future work will focus on enhancing signal detection, particularly within the keyhole region, and improving the durability of optical components in harsh welding environments. By addressing these challenges, we aim to further refine our plug-in OCT system, ensuring robust and reliable performance for advanced laser processing monitoring. Thank you.